the whole machinery. So the exponential distribution, remember, it's tied to the Poisson. The idea is that the Poisson counts the number of occurrences, the exponential counts the time between occurrences. The Poisson is discrete, exponential is continuous, but they tell you the same thing. And this is the PDF for the exponential. And you might think that, well, that looks awfully similar to the normal. It turns out that this one is extremely friendly. In fact, when you take the derivative of the CDF, you can pretty much do that in your head. The derivative of an exponential is just the same thing times the derivative of this thing. So you end up with that, you leave that piece, and then take the derivative of this, which is minus 1 over mu. The minuses cancel out, and you have 1 over mu e minus x naught over mu, which you'll recall from the previous page is the PDF. So in this case, very different from the normal. You plug in, and you get probability of interest. As an example, you can look at the time between arrivals at a car wash. It can be anything. It can be arrivals at a car wash, particles from an X-ray machine. It can be, well, there are all sorts of operations management processes where this is central. All you need to do is calculate the mean time between arrivals. Can you do that if you have data? Pretty straightforward, right? You just literally count. As long as you have the time of arrival, it's easy to find the mean time between arrivals. That's all you need. You do, it's true, need to check that the exponential distribution is okay, but it often is remarkably good. Okay, so plugging in, you have a mean time between arrivals of 3 minutes. You want to know the probability that the time between two successive arrivals is 2 minutes or less. So you plug in 1 minus e to the power of minus 2, 2 is the x, divided by 3, which is mu. And this part you will need a calculator for, I'm pretty sure. You get a 48.66% probability that it's going to take less than 2 minutes. So you can again draw, and this right here, where the PDF crosses the y-axis, just plug in x equal to 0 in the PDF, and what do you get? Here. If x is 0, then this is e to the power of 0, which in fact is 1. And so f of x is just 1 over mu. So what do you have on the y-axis? You have 1 divided by the mean time between arrivals. It's fairly straightforward to read for that reason. This just reiterates. Poisson distribution and then exponential. If one holds true, the other holds true. So just use whatever is easiest. Just as an example, or forewarning perhaps, this is a traditional type of problem you get when you study operations management, or in particular this topic of statistics. You would get a problem that utilizes both aspects. And that is the exponential, and that covers all three distributions. So let's do a problem with the exponential. We're told that the time between phone calls at an insurance claims office has the following exponential probability distribution. Of course, if you were actually told that this was the probability distribution, you would know that it was exponential. Okay, it might be easier to write this as follows. And remember, the general function so the first question is, what is the mean time between phone calls? What are we looking for?
Mu.
Mu. Good. And can you tell me what that is? 2. And how do you get that?
Looking at the formula and
Right, so you realize that the only way that you're gonna get mu is simply saying, well, either one of mu is 1/2, or just notice that mu is equal to 2. Good? What is the probability of having 30 seconds or less between phone calls? Well, let's draw this thing. I guess we put X here. Where does this cross? Very good. 1/2. And so what are we looking for? So in terms of our formulas, that would be probability of
X less than 30
x less than
or equal to 30 seconds.
0.5,
0.5. Why?
because it's one,
You're right.
because we're going it by minute.
Exactly. What we're dealing with is measured in minutes. We're given a question in terms of seconds. You just have to translate. The reason that I mention it is that it's a very, very common source for error, right? You have to be somewhat careful and compare apples and apples. All right, so this, we know we can just plug in 1 minus e to the minus 0.5 divided by 2. And that turns out to be 1 minus 0.7788, 0.2212. There's a 22% probability for that too. 22%. Any questions on that? Okay, if there are no questions, what is the probability that there's a minute or less between phone calls? What shall I write?
1 minus e to the negative 1/2.
Very good. And before we go further, let me point out something. If this is 1/2, and we were interested in that area, and now we're asking for 1 minute, so we're interested in this whole area. What can you tell me about the probability? Okay, it's going to be pretty close to doubling, but is it going to be more than a doubling or less than a doubling?
Less than double.
Okay, so it's going to be slightly less than a doubling. And since the probability we're interested in is 22%, we're looking for a probability roughly
35,
40%. As it turns out, that's magically prescient. This becomes 1 minus 0.6065 or 0.3935. Very close to your expectation, right? And when you can just look at a graph and immediately tell me or tell yourself what you expect to find, it's much easier to check your work. You're far less likely to go wrong. Okay, finally, 1, 2, define the probability of 5 or more minutes. So this area. What can we say about that area? It's a lot less than 50%. At the very least, it's remotely correctly drawn. I'm sorry? I missed the point. Were they? Oh.
With you.
Well, as long as they're not laughing at me, no. Well, okay, I'd agree with that, it's a lot less than 50%. But at the very least, we can say that, there's gonna be some probability between 1 and 5. We already know that 40% of the probability is in here, so you have some idea what you're looking for. And as it turns out, this isn't that hard. Probability that x is greater than or equal to 5 is equal to what? Lar?
1 minus e to the,
Very good. 1 minus the probability that x is less than 5, which is 1 minus e to the what?
minus 5 over 2.
Minus 5 over 2. Excellent. And then 1 minus 1, of course, is 0. Minus minus is positive. So that's just e to the minus 2.5, or roughly 0.0821. Right. So again, in line with expectations. Okay, so those are the continuous probability distributions we're going to work on until we start with different types of sampling distributions. And we do have a review problem for next time, but before we go there, again, compare and contrast discrete to continuous. What are the differences?
Discrete has definite values, continuous could have any.
Okay, and what can we say about the probabilities? With discrete probability distributions, each outcome that's remotely possible will have
Has an associated probability.
an associated probability. And what is the associated probability with every outcome in the continuous distribution?
0.
0. Right. Okay, so it's that whole infinite precision thing that throws people. What you need to remember is the notion that the exponential measures time between arrivals of different sorts. It can also be the time it takes a light bulb to go out, things like that. The normal measures a lot of things. And the uniform is really just a good illustration and sometimes used for reliability. But it's a very good idea when you're studying this on your own to just keep reminding yourself where you can use the different types of tools. Because remember, if they are tools, they are used for a lot of things. But unless you can recognize when it's appropriate, you're never going to reach for these things. Which you may not anyway, but they are at least available. Any questions on the topic of today or last week? Okay, in some of the other classes there were questions from problems or anything from previous weeks? Alright, well in that case we can take time for projects or